Hi, everyone. Welcome to this session on building a high volume conversational AI for health insurance. Hope everyone's having a great conference. Hope you enjoy this last talk of the day. Hope everyone can, in fact, hear me. So, I'm going to walk you through a brief case study and tell you some of the things that we learned, some of the things that we encountered doing this project. And if you want to learn more about me, my name's Andrew Freed. I work at IBM and I'm an author of Conversational AI, a book available on Manning.com. But let's start with the use case, what our project was about. So our target audience was medical providers that are contacting a large U.S. health insurer. And I'm fairly sure the audience is aware, but US healthcare is exceptionally complex. Um, Medical providers are very frequently calling health insurers for very routine pre service inquiries. There's a lot of calls per day. In fact, when you go to the doctor's office, you can often see someone behind the desk who is literally on the phone all day with health insurers, making calls about their patients. Um, and there's four primary types of calls they're making. The first is to make sure you are eligible for healthcare, that you in fact have some sort of healthcare coverage. Um, Additionally, if you go in for a procedure, they're going to find out what's your benefit. So if you go for an office visit, how much is that going to cost you? If you're having something involved like a surgery, they may do an authorization, which is the health insurer making sure that they're going to allow the provider to do this service. And then once the service is actually done, the provider is going to file a claim with the insurer, and they'll probably call back to the insurer to make sure that that claim has been paid. So all of these calls are ultimately serviced by essentially one API call by for the insurer, um, and the call is to gather the information we need to make that call and then read the information back to the provider. Just a quick architectural overview of how this actually works in practice. So this is a voice solution on the phone. So a provider is going to call in. They're going to say something like, "I need the claim status for a member." The first architectural component is a speech to text engine. Our AI services are working with text, not speech, so we need to convert that audio stream into a text stream. I've noted here that the speech service can make mistakes. In this case, it mistranscribed claim for claims. Um, so our conversational system does have to be resilient to certain kinds of mistranscriptions. After we've got the textual representation, we send it through an orchestration layer. The orchestration layer on the request side has one job, which is to mask any sensitive data. Um, in this utterance, we can see the sensitive data is the member's ID. We don't want to share that too broadly, so we're going to store that in the SOE only. And then Watson Assistant is going to take a look at this textual utterance and figure out what's the intent behind the utterance. In this case, it was kind of easy. It was a claim status. So now we need to figure out how we're going to respond to the user. So the first thing is Watson Assistant is going to decide the text that we need to play back. And we're going to say, hey, what's the claim ID? That's the next step for figuring out a claim status. The SOE doesn't need to do anything with this. It'll pass the utterance through, but the SOE will be aware that the next thing to come back from the caller is going to be a claim ID, a sensitive piece of information that it needs, that it can't send on to Watson Assistant. And then, of course, since we've been working in text, we need to convert it back to an audio stream for our caller. So we will convert that text into an audio stream and play it back to the caller. So I'll walk you through the dialog flow that's been implemented for this. So the first interesting thing is that there is no dedicated phone number for this solution. Our insurer has essentially a vanity phone number. You can think of it as 1-800-4 Watson. And that number serves all kinds of different callers. And we are interested in medical providers. So um, behind the scenes, the telephony does some sort of um, routing logic to make sure that, hey, if it's a phone number it recognizes is coming from a provider's office or from a hospital, that's going to come on through. Um, if it's a number that knows belongs to a member, it's going to deflect that somewhere else, right? Members have a different call center solution that they go to. But assuming we've got the call routed into us and we can actually handle it, we are going to. Oh, I'm sorry, I'm not sharing properly. Um, let me try again. Thanks for letting me know. I'm gonna try it this way. Okay. We'll lose the animations, but we'll try to go with it. So again, we're first making sure the call belongs to us, and then second, once the call comes in, we're going to ask the user what they want, and this is our intent capture phase. So we're going to figure out what they want. We're going to make sure it's something we can handle, and assuming it's one of those things, we're going to read them a disclaimer and start an authentication process. Not just is our healthcare complex, but we also have privacy laws like HIPAA and other regulations that says you just can't give information out to any arbitrary person. So we're going to do a couple different kinds of authentication. The first is a provider authentication. So we're going to make sure you are who you say you are. We're going to ask you for two numeric identifiers to identify the provider. And then we're going to ask you to validate that you have access to the member that you're calling about. So typically, this is information from the back of the member's insurance card. We have a primary of an identifier and a date of birth, but we also have secondary identifiers that we allow. After we've authenticated the member and the provider, now we can actually serve the actual intent. And you can see here on the left-hand side that all of this authentication and grading and intent capture, this is all common no matter what intent we're actually dealing with. So we put this in a single Watson Assistant code block. It's called a skill in Watson Assistant, but you just think of it as a code block. Once we've authenticated the member, we route out to individual skills to handle each of the individual intents. So I talked earlier that we've got the 4 primary intents. One of those intents, in fact, has 2 different flavors. And from a code point of view, those are all isolated from each other. Right. So the eligibility code flow is separate from the benefits code flow, which is separate from claims and so on and so forth. So in the Watson Assistant parlance, these are all separate skills. And then we bring the conversation back together through a common skill called the closure skill. This is going to handle things like, hey, we're going to create a Salesforce ticket at the end of the call. We're going to read you that number. We're going to ask you if we can help you with anything else. And if we've completed your call, we're going to ask you to take a survey. So we implemented the dialog this way so that there would be a consistent user experience, so that no matter what you were calling for, you would have a predictable call flow. So the next thing we did when we were in production is to start reviewing the how well the classifier was working. And you can see 2 different outputs. One is our confusion matrix, and then the other is a heat map of the accuracy. Um, so one of the interesting thing about providers is that since they make so many phone calls, they're almost robotic in the way that they use the system. Once they figure out an utterance that works to get what they want, they use that every time. So it turns out there's not a lot of variation in the inputs that we receive. So for the primary intents, eligibility claims, authorizations, and so on, we've got a very high accuracy on those. One thing that's interesting is you'll see this lightish green box, large green box towards the top right that has no intent in it at all. And it turns out that very often that initial telephony routing that we were talking about doesn't always work. And we'll get an utterance that is completely out of bounds from what we handle. And typically, this is a member calling the system, and they're saying something like, "Hey, this is Martha Jones of West Kentucky, and I need help with my husband's prescription." And this is way more verbose than our typical callers are, and it's not aligned to one of the intents. So we identify that this is in fact a member, and we get them routed out. The other training thing that we focused on was the speech model training. So you saw earlier that there was a large volume of authentication information that we took, and so for each of these different expected utterance types, we have a dedicated speech model for each of these. So on the first turn, we expect an intent-based utterance. We have a model for that. For our provider authentication, two different IDs. So we've got two different speech models for those. Um, and if you keep moving on from the right-hand side, you see models that are dedicated for each of the major inputs. And we found this is what gave us the best accuracy overall for the solution. So the first thing we did before we trained any models is we took the base Watson model out of the box, and we saw, look, how does this thing perform on a test set of utterances? We worked with our customer to build a test set, and we do this because we want to make sure when we train the speech model, we're not actually making it worse. We took between a few hundred or a few thousand utterances for each of these different types, and we took a baseline. And then the second thing we did is we start customizing a model and testing it. And I won't read the individual results, but you can see that for each of these, by doing a customization, we were able to improve in performance. And you can also see in the bottom row the size of the test set that we are using. So considering that over the life of the bot, we're handling a volume of millions of calls, um, a test set in the size of thousands of utterances kind of makes sense for that kind of scale. To walk you through one of our most difficult speech challenges, so we had one particular identifier, which you can see was an 11 character string with a mix of alphanumeric, alphabetic, and numeric. So this hits several of the speech to text challenges. It's very long, and alphanumerics are very easily confused. If you look at that position number 3, um, the character could be a 3, an E, a C, a D, a T, all letters and numbers that kind of sound similar. So even for humans, this is a very difficult task. And you can see that out of the box, it was very difficult for us to transcribe this accurately. So the first thing we did was we tried a bunch of different speech models. Um, if you look at that set of rules in the lower left, it feels like, hey, a grammar would be the perfect thing. A grammar is essentially a set of regular expression rules that you can apply. But it turns out that wasn't the best that we could do. We did better with other types of speech modeling. So the first thing we learned is, run multiple experiments. The second thing that we learned is that, hey, when the speech has done its best, there's still room to do a post processing. So at the very at a high level, what we did was we considered we asked the speech to text to generate not just its best guess, but several guesses. And we would look at each of the guesses it generated and first look at, does it even match the grammar? After it matched the grammar, we would attempt to validate each of those guesses against a backend API to see if it was a valid identifier in our insurer system. And there's a benefit and a cost to this. The benefit is that you have a higher chance of getting something right. The cost is that the more API calls you make, the slower it gets. So we also plotted that out to figure out, hey, how many does it make sense to keep trying before we go on to the user? But the takeaway here is that you should try multiple experiments, and sometimes the answer is to go outside of the service itself. So we definitely found that, as in all AI projects, continuous improvement is the name of the game. Our customer in the beginning was expecting a straight line result that we would hit, you know, a very high performance target right out of the box. As you practitioners know, it takes a lot of iteration going back and forth until you get to what you need. So there are plenty of additional resources where you can learn more about the project that we did. We wrote a huge series of blog posts, but you can also find a lot of this in my book. And if you go get the book at manning.com, please take with you that code FreedPC, which will give you a nice little discount on the book. So in summary, we learned a lot of lessons as we built this, but in the end, our conversational AI solution was able to deflect millions of phone calls from a call center. We were able to answer these phone calls in an AI solution and give users their answers more quickly rather than them having to be on hold and waiting for a human agent. And as always, this is a continuous process to build, train, and improve a system. So with that, I will take your questions in the comments here or the Q&A section. All right. I believe I'm looking at this right. I see messages where I had my screen sharing wrong. The QA section is blank. Um, Appreciate the note there, Joseph. So I know this is the end of the day for folks who were at the session. So I hope you had a great conference. Um, Again, I'll stay here another minute or two, I guess, to take questions if you've got them. But otherwise, thank you all for attending. Hope you have a great evening, rest of your day. Oh, great. A question here. So how good is the recognition of the IDs now? So it depends on the ID type. I would say for the numeric ones, they're sort of the easiest ones. That recognition is very, very good. I think we were in the high 90s on some of those. Um, it depends how much pattern recognition you can apply ahead of time. So I showed you sort of the worst one, which had the numbers and alphanumerics and alphabets all kind of mixed up. Um, but I would say for generalized predictors, numeric is better, shorter is better. Um, and I think for most of these, we were in fact able to get them somewhere in the 90s. And again, depends on the specific ID and the length. Thanks, Rolf. Great question. One more question. Okay, recognition rate for the worst ones. So I think at the worst case, we were about 30%. Sorry, that's a 30% error rate. So a 70% accuracy. Yeah. So 70 was our worst case. And I'll also note that um, the designers built the conversational flow so that we only use that one as a fallback. So one of the things we learned was um, to optimize the call flow for what people had on hand, and if there was two pieces of information they were likely to have, we would tend towards asking them the one that was easier to transcribe. So in that case, again, the 11 character one that was, lots of alphanumerics. Even for that one, there was an alternative ID that was a nine digit numeric. So for that, we would ask first for the 9 digit numeric, and if they didn't have it, then we would go to that 11 digit one. And that way, we're sort of almost hiding the worst ones to increase the chances of success for both us and the users. All right. Glad I answered your question, Rolf. It looks like the questions are slowing down and people are trickling out of the chat. So I think we'll stop the broadcast here. Again, thanks everyone for joining. Enjoy the rest of your day. Take care, everyone.